we talk about mood and variance, here we've got mood and how it varies. When we just say how something varies, what are we talking it varying around? I don't say it, but it's varying around something explicit. When I say, how does mood vary? In lay terms, I'm saying, what's the spread of all the mood scores? But in stats language, when I'm saying, how is mood vary? We're saying, how is it spread around the mean? You got to be a little bit careful, as you'll see a little later. Variance is a word that we play with in stats to mean different things. So variable on its own, mood, varies around the average of mood. And the same thing happens with motivation. It varies around the average of motivation. But then we can also look and say, how do they move together, co-vary together? And we can see just by looking at this visual that when mood goes up relative to its mean, it's varying up from its mean, Motivation also varies up from its mean. When mood goes down, meaning it varies down from its mean, the same thing is happening to motivation. So it's varying, spreading away from its mean in the same direction to roughly the same degree. That's what we mean by covary. Don't forget that whenever we talk about variance of a variable, it's always relative to the anchor point, which is the mean. So we can calculate, well, how much covariance is happening relative to how much variance is happening. So let's look back at this graph we just looked at. In this example, look at person H. This distance, the amount point H is above the mean, is almost exactly the same as the amount that point H is above its motivation mean. But what happens if the point were here? Then they're both varying in the same direction away from their mean, but motivation is varying a little bit more. So in this case, they're varying almost in exactly the same direction and the exact amount, which is why we end up with a correlation that's so high. Because Pearson R is a ratio of how much they're going to vary together, meaning in the same way and the same amount away from their mean, relative to how much they do that separately, as in not in the same way. And someone asked if we could calculate it together or manually, and yeah, you can. I'm not gonna make you do that on the exam, but yes, you certainly could. Conceptually, if you think of all the spread, so here's the mean, here's the mood mean or motivation mean, here's the mood mean. If you take all the spread of mood and all the spread of motivation, the part that overlaps is that covariance. Now, why did I color it twice?
They both exist. One of those variances exist.
Both of these variants exist. You've got this variance and you've got this variance, and they're going to overlap in the middle, and they're both going to be there. So that overlapping space describes the covariance. That's really important. If we wanted to calculate it manually, you could. You would just figure out, first of all, well, how far does every point deviate from its mean? That's the first step to calculating any type of variance. And then you would calculate the sum of squares for X, so for mood, the sum of squares for Y, which is motivation, and that's all you need for this part, the bottom. But you need one last thing, which is you need the covariance. And that's how those, it's not how the sums of squares move, it's literally how those deviations move. So it's taking the mean, if you look at person H, it's taking person H's score on mood minus the mean and multiplying it by person's motivation score on H minus its motivation mean. And then it's doing that for all of the points in your data set. So you end up getting what we refer to as sums of squares XY. So see this? This is a deviation. Sorry, here. These are the deviations. How far away is H from its mood mean? And how far away is H from its motivation mean? Then let's multiply those together. That's XY. When we add them all up, we get sums of squares XY, and then we can just put it into our R ratio. Yeah.
No, there's no stupid questions. This one feels silly. When we do the circles and we're talking conceptually of variance, what's inside the circles? It's variance. So what, I know you said like we use the word variance to mean.
The amount of deviation that each point has from its respective means multiplied together. It's this.
So when they overlap, does that mean that it's the same distance from their mean, or exactly what does it mean for
It
it?
doesn't mean that it's the same distance, is that there's some degree of pattern of movement that's related to each other. Yeah. But for example, if I gave that H example, for person H, if it deviated this much, I'm talking standard units, if it deviated this much from its mean in mood and this much from its mean in motivation, then the overlapping part would be the part it both deviates. Yeah.
I have a quick question, also maybe a silly question. Can you remind me why we square?
I'll get there.
Okay.
Yeah,
Thanks.
to get variance explained.
Yeah.
Yeah, so in order to answer that question, she asked, why do we square little r to get variance explained? In order to do that, the most critical thing that you understand is this part, which is to start, I'll use the colors I use, which to start, there's variance in mood and there's variance in motivation. I could study those separately. If I'm interested in covariance, all I'm asking is which parts of those overlap, and both colors are there. Do you see that? Yeah. So all I'm saying here is how much do these two things covary? That's different than saying how much variance in one of them is explained by the other, which is what when we get to R squared. So what can we learn from correlation? One, strength and direction of covariance. Strength meaning the absolute value from 0 to 1. 1, super high correlation, 0, no correlation. Direction, positive or negative. Does positive means they move in the same direction? Negative means they move in opposite directions. We can also learn the amount of variance in one variable that's explained by the other. But it's always just two things. When we're talking about correlation, we're only talking about two variables. So if I want to know the correlation between ASL and SCC, that's as if all these other ones don't exist. If we wanted to consider the other things, we need to bring regression in. And potentially, the reason I underline potential is that it can give us insight into predictors that are really related if we're going to use them later in a regression model. Now, not all the time. If we see a correlation between predictors of 0.92, that's a pretty clear sign we're going to have an issue. But what if we have a correlation of 0.70? We don't know we're going to have an issue. But if I found an issue and I went back to this as a way of explaining, it's not we look at the correlation table and then leave it alone. Correlation table is something we can use after we've run our models to help explain what we saw. If we find issues that in our model, we can go back to the correlation table and I can go, oh, that might be why that happened. Good so far? So what do I mean by the three things we can glean from correlation? First is strength and direction of the covariance. This will answer your question, Hannah. So we have variance of the orange variable and variance of the purple variable. And the part where they move together is this overlapping part. It looks like this. Notice no line. Correlation is not a predictive model. Let me make that clear again. Correlation is not a predictive model. It is just descriptively explaining the strength and direction of two variables. That's it, okay? I'll hit on that again when we move from correlation to simple. We can also know the variance in one variable that's explained by the other. Covariance tells us the strength and direction that both move together, purple and orange. If we only want to know how much of this orange circle gets explained by purple, then I don't care about purple's variance anymore. I just want to know what percentage of this orange pie gets overlapped by purple. So I have to square the R to get rid of essentially the purple double counting, the correlation. So to get variance explained in one by the other, I need to square my little r. Questions? Yes.
So the variance explained for, in this case, the orange and purple are exactly the same.
Correct. Yeah, no, good question. The variance explained will be the same. So if I say how much variance in orange is explained by purple, that's identical to how much variance in purple is explained by orange. Correlation is non-directional. It's just that one is explaining covariance and one is variance explained. How they both move together is covariance, so both of their variances are there. Variance explained is literally just taking one of the variables and saying how much of that pizza and how much of that pie is eaten by the other variable. Yeah,
Got a really dumb question.
love them. Can we not preface every question today, but this is a dumb question? Yeah,
Why isn't r squared not just r divided by 2?
because to get this, we didn't times it by 2, we squared them. We have to undo what we did. It's a good question, it's not a dumb question. To get this, we took the deviations of x and the deviations of y and we multiplied them together, which produces a square term. So to undo that, we have to undo them. So if you multiply something by 2, what's the opposite of that? Dividing by 2. If you square something, the opposite of that is square rooting. When you get a variable, when you get a number that's under 1, you can square it to get the opposite of that. It's just the mathematical inverse operation. And then the last thing that we can glean is potential multicollinearity. This is not a binary decision. Somebody asked this in the review questions. Every set of variables, every set of predictors has some degree of multicollinearity. It's just the degree to which two predictors are related. It could be not at all, it could be a lot. It's only when does multicollinearity become a problem. Really, what we talk about is collinearity, is what we call it when we're not worried about it. Really, and multicollinearity is what we call it when we're worried about it. But really, all predictors are usually related to each other. It's just how much. So if our R is, the larger the R, the more of, think of a beeping signal, a honing signal. It's, if you get an R of 0.2, there's no signal. But as that R goes up, the signal becomes a little bit louder. And that signal is just saying, check on this, check on this, check on this. It's not saying do anything now. It's not saying stop, don't put them, unless it's like 0.9 and it's blaring, stop, these are the same things, stop. Otherwise, it's just giving you a little warning sound. Okay? Now let's do these from the check-in. So the question was the percent of variance in needs. By the way, these are the percentage, class percentage that we did. This is not a diss on the TAs, but you guys did much better than last year. The TAs did great last year. I'm not worried, I wasn't worried about you, but overall y'all did, you're sitting pretty for Thursday. It's in a good spot for Thursday, actually. So this is the percentage we got class-wide on each question. The percent of variance in need satisfaction explained by identity integration is what? So if we go need satisfaction, by the way, if you're having trouble reading a correlation table, this is how I do it. I just take the two variables and I draw need satisfaction and can't do it that way, just to make sure I don't misread for some reason. So a lot of you said 0.47. That's the R. If this is need satisfaction and this is identity integration, if we say 0.47, we're double counting that variance. We're squaring that variance. So to get variance explained, we need to square R squared. We need to square R. What do we get? 20%? 20%. 22%? Okay, yeah.
So I'm gonna ask the covariance ratio.
Tell me. Yep. But if we're talking about covariance, we wouldn't ever say covariance, because if you think about what the R correlation is, it's actually R isn't covariance. It's covariance relative to how they vary on their own. So I would never say what's the covariance. I would just say what's the correlation. Yeah. Yeah. Yep.
Sorry, so I can get this out of my brain.
Good.
That represents two spheres, not two circles. That's why I'm having a hard time. I'm seeing it as,
It doesn't represent anything concrete. I'm just drawing a picture. It actually represents distributions around the mean. It's all the values of, it's how, if you think about what it's really representing is how do all the values of need satisfaction spread around the need satisfaction mean? And how do all the value of identity integration spread around the identity integration mean? And the part in the middle is the way that if you are a person in my study and you're a little bit above the mean in identity, and that also makes you a little bit above the mean in need satisfaction, those are traveling in the same direction.
no, I understand.
That's the part in the
I
middle.
understand it conceptually. It's just
Yeah.
Visually, I see it as the area and. I
Yeah.
pictured it as three-dimensional now. I thought I got it.
I'm literally just kind of drawing it, it's a pizza pie. It's nothing, it's not meant to represent reality of space. All right, now let's build regression models. So we've got correlation, it's descriptive. I'm still gonna ease us from correlation to regression here, so give me a second, we're not gonna leave that entirely behind. All right, so the difference though is with regression or with correlation, we're really just describing. We have two variables and we're saying how strongly and in what direction are they correlated. When we're doing regression, we're usually trying to explain, predict, or model something out there in the real world. That's the move from descriptive to inferential stats. When we run regression, we do not really care about our data are not our primary focus. The world out there is our primary focus. We're using our data to make inferences about the world, but we've clearly landed in inferential land. And that's a really important thing to remember, because that's where things like hypothesis tests and error and t-tests come in. None of those make their way. There's no such thing as error in descriptive stats. Things are what they are. If the mean is 4, if I survey all of you and I'm how confident are you in Thursday's exam? And the average is a 5.5. Is there any error there? No, it's just 5.5. It's descriptive. Now, if I use that to predict your exam score, now I'm introducing error because I won't be all the time. That's the difference when we move to correlation to regression. So what do we do? What are we really doing when we're trying to explain, predict, and model from an inferential perspective? We're estimating. So I use this word estimation. What do I mean by that? Well, we start with a model of what we think is happening in the world. And we tell R, in this case, hey, this is our model, and here's our data. Those are what you've got to work with. That's it. You don't get to change my model that I've specified, and you can't change my data. So then what R is going to do is it's going to fit the model to the data as best as it can, and it's going to, here's that keyword, bless you, estimate parameters. Estimate means figure out, it's not a guess, it's figure out or give you, and parameters are what? What's up, first day of 308 day?
Population.
Yeah, give me more than just the word population. They are numbers, yes, that represent phenomena that are happening in the population. So a B or a beta is a parameter that represents a relationship out there in the population. Standard error is a parameter that represents how much error our model would get. Are we good? So we fit the model to the data, and then we use those results to test hypotheses and theory that we started with. And then we do it all again. That's called research and stats. All right. So this one, now, I will tell us, it's not with this people, I have no idea. This one, I missed shooting archery. My mom was an archer in college, I just found out. And it's everybody hit the target, but we were on the outer rings. That makes sense? As in not specific enough, not clear enough, not quite hitting the bullseye, but not being, it adds things together and finds a line. We weren't off, we just weren't on enough. So the two questions were, what's the method called? And then what is the goal or process of this estimation method? So remember, the estimation method is the process that finds those values. Specifically, What are the two parameters that this estimation method's gonna give us that we really care about? Slope and intercept. Those are the only two things we need to make a predictive model. If I have an X and a Y, what are the only two things I need to draw a line? I need to know where I should start. Should I start here? Should I start here? Should I start here? So here, I'm gonna start here. And then I need to know at what angle I should draw that line. Now I have a model. Now I can predict things. Hey, if Heather is here, I predict her Y to be here. If Sean is here, I predict his Y to be here. The only parameters I need to predict in a model are slopes and intercept. Those are the two parameters that it's going to generate or estimate for us that are most important. So what is the method called? It's called ordinary least squares. Not least squares, not mean squares, not ordinary squares, ordinary least squares. Do I really care that you know the name? No, I really care that you know how it works. Now, a lot of us said it finds the line of best fit. Not wrong, but every estimation method does that. Every estimation method estimates parameters that best fit our data, but they don't all do it in the same way. Some weight certain things differently. Some, we won't get into others, some use robust standard errors. There's different estimation methods. So if you just say it estimates the line of best fit, that doesn't differentiate OLS, ordinary least squares, from the other types of estimation we don't use in regression. Yeah.
Is it a more conservative estimation method?
Say it again.
Is it more conservative? It doesn't take, similar to when we did the different post-hoc tests and stuff?
No, it's not more conservative. That's actually less conservative. It's the standard, nothing is wrong. It's the same as maximum when your data are normal. Yeah, it's your, my first thing is it's your processed white bread of estimation methods. Yeah. If it's like you don't mess manually with the estimation methods, this is your default. So how does it do it? It selects parameters. It doesn't find a line. It doesn't go in and draw a line. What does it actually do? It estimates what? Two things. Yeah, it estimates parameters, specifically intercept and slope. It estimates the parameters or the line, that's fine if you want to say that. But where does it decide how to put that line? It decides where to put that line by placing it where it minimizes the sum, so the total, of the squared deviations. Deviations between what? Deviations and residuals are kind of the same. Deviations between, but what is your point called in statistical language? Observed data and predicted. What's another way of saying that with the word residuals? It's just model residuals or model error. So it's estimating parameters that minimize the sum of the squared model residuals. Meaning, really concretely, it's making the total of all of these squared values as little as possible, okay? If I move the line, it's gonna be bigger than it has to be. So it's giving me the parameters. It's not giving me a line. It's estimating the parameters that minimize the sum of the square residuals. Or if you really just said that minimize model residuals, that would be fine too. But what I care that you understand is that you've got what the model predicts with the estimates it gives you. And you've got observed data. And the whole point of OLS is make those as close together as you possibly can. Yes, JJ. I'm not going to get into how robust maximum look. Yeah, their mathematical underlying process is super different. It can weight different predictors. It can weight points that are better fit than other points. There's lots of different estimation methods. Yeah. Cool. And these are the parameters that get estimated. Intercept, slope. How are they related? Intercept is just your starting point. It's where's y gonna be when x is 0, or x is at the y-axis. And then slope is, well, what's gonna happen from there as I go up 1 point in X. As I go up 1 point in X, Y is gonna go this much. Then I'm gonna go up 1 point and it's gonna go this much, then up, there's your slope. Starting point, slope. Questions at all about this?
So you use a different estimation method, you kind of,
We're not worrying about different estimation methods.
No, but-
You've got an exam on Thursday.
no, I mean,
Yeah.
I just wanna ask,
Yeah,
is that, we no longer quite in regression land?
you could be. You could be. Yeah, you totally could be, but we're just using standard regression estimation. Other questions about this? Good? All right, so speaking of, related to this, so let's review. OLS estimates what? Parameters. Good. What are the two parameters it's estimating? Slope and intercept. And what do those two things make up? A line, the line of best fit. That's the colloquial lay term. But those two things are the actual parameters that get estimated. Those are our what? That line represents our what? Our model. Good. Is our model perfect? No. What's the distance between our model, which is predicted, and our actual points, which are observed? What's that? Residuals, error, whatever. Good. So now let's think about question 5, which is there's more variance in your predicted Y values than there is in your observed Y values. So your observed Y values are your actual data points. Your predicted Y values are going to be what your model predicts. Which has more spread? Yeah, observed. Your observed values are always going to have more spread. Because here's what the model predicts. They're all on this little line. But then guess what additional spread you have to add on to that? All your error terms. So there's more variance in your predicted Y values than in your observed is false. There's more variance in your observed scores than there is in your predicted. Now let's go from correlation to regression. The question, how does big R squared, B, beta squared differ from correlation to simple to multiple regression? Some of this is in here, but here's what I'm going to suggest. All of the answers to that question are in all of the decks we've had already. I highly suggest you make yourself some sort of way of answering this, because if I just tell you again, it's different than you generating it for yourself. So as a study technique, think about what are all the statistics and parameters that we've looked at between correlation, simple, and multiple. How do they change? How are they the same? We're going to go through it, but do it for yourself rather than just being, oh, look, it's on the slide, because that won't actually internalize. So as we move from correlation to regression, I want you to think of the following two variables: interpersonal conflict, okay, so fighting amongst people, and energy depletion. So as interpersonal conflict goes up, what happens to energy depletion? You ever fought with someone before? Let's try that again. As interpersonal conflict goes up, what happens to energy depletion? It goes up. Energy depletion. Energy goes down, but level of energy depletion goes up. It's a positive correlation. So researcher A examines the correlation between those two things. Researcher B runs a simple regression with interpersonal conflict predicting energy depletion. First of all, draw those two models on your paper, somewhere in front of you. What's the difference going to be in the model?
Errors.
Yep, one-sided, two-sided curved. Great. Now my question for you, how are these the same or different? It's not a trick question. The differences and similarities are nuanced. How are these? You should be able to explain how these are same or different.
They're same or different in the way that I explained them. So I guess I'm kind of not assigning causality, but I'm hypothesizing in the second one that one is causing the other. I'm assigning a predictive nature to that relationship versus in researcher. I'm just saying there's a relationship.
Good, that is one huge difference. It's just, now, is that in the data or in the stats or in the R or in the anything? No, where is that? Theory. So one big difference is how we are thinking about it from a theoretical perspective. Doesn't show up in the data, it's in our head and in the literature. As
Yeah.
Em said, researcher A is saying, I just want to know how these two things move together. Researcher B is saying, I am thinking about how the first one happening causes changes in the second. Even though I know statistically I can't prove that, that's theoretically how my brain's working. Good. Anything else? That's how they're different. Yeah, Kayla. Good. She said the correlation is going to give us a descriptive stat, as in just how are these correlated? And the simple regression is going to give us a parameter we can use to predict somebody's energy depletion if we know their interpersonal conflict level. Good. That's another difference. We've got two differences. What about similarities? There's a big similarity. Huge.
They're both only two variables.
So yes, other than being the exact same variables, which is on the slide, thank you, Alan. What else? What statistically will be the same?
The R will be the same.
Yes, the R will be the same as what?
Big R and small R is the same.
Big R and small r is the same. What else?
It's also the
Beta.
same as the beta.
Yes, good. So now researcher A reports a correlation of 0.52. Researcher B runs a standardized coefficient of 0.52. They're the same. We're still asking how things move together. They move together. I haven't changed the variables, so they don't change how they move together. And we're still just considering those two. We haven't introduced anything else. So if you think about a correlation, how things move together, that's kind of the slope. As something goes up, what happens to the other one? Same concept. So then are these things telling us exactly the same thing? Not quite, as we just got to. And here's one way of thinking about how they're different. Look at these graphs. Look at the dots only first, if you can. See past the red line for a second. The dots are identical, as in the correlation is the same. But the correlation is just describing how interpersonal conflict and energy depletion move together. There's no line. You see that? We have to draw lines in correlations, but that's just for us. We're not actually making any sort of predictions. We're not using correlation to say, if Lexi is a 4 in interpersonal conflict, what is she going to be in ego depletion? We don't use correlation for that. We only use correlation to describe. But we can use simple regression and generate our beta and an actual regression equation with an intercept and a slope, and use it to predict someone's ego depletion based on their conflict. But the relationship between those two things doesn't change. So the beta can't be anything other than the little r, because the relationship stays constant. It's the same, they're the same variable. And just if I want to know variance in one explained by the other, how do I get that from here? Same thing, square the beta. Now, the one last difference is look at my assumptions. Why is homoscedasticity not an assumption of correlation? Because you don't have any error. Beautiful, I don't know where I heard that. Yeah, you don't have any error. There's no line, there's no prediction. So there's no gap. It's just how do these two things move together? So there's the entrance of error doesn't come in until we have a predictive model. Cool? Does that help a little bit? Yeah.
Sorry, this might be a tangent, but how do we get a t-test for, how do we get a significant testing for correlation then?
You can blow correlation up to rho, which is the population level correlation. But we don't treat it as we're really treating it as descriptive in the data.
Jess, that
Yes.
was really helpful. Can you talk about multivariate normality versus univariate normality?
Well, in the assumption section,
Great, thank you.
but it's there. There's a slide called "There are two types of normality." Yeah.
Yeah,
Does the inferential graph having a line modeled instead of no line, you kind of explain how beta can be viewed as the slope? Does that kind of have to do with that in like model Y?
In model Y.
Not Y, model Y.
Oh, yes, 100%. That is exactly why. Perfect, 100%. Yep, this line is the model that is best fitting these points. And beta is the slope because it's telling us exactly what happens in the same way as correlation does. As X changes, what happens to Y? That's the definition of slope. It's just telling us in a very specific unit, which is standard deviation. Cool. So here's another way of looking at it. Again, these are nothing but just drawing circles. They don't represent, they just represent all the variance. So here's your outcome. Here's your predictor. There's your correlation. It's got the variance of X and the variance of Y in it. It's how they covary. It's both colors. Little r. If I change that to a simple regression, it would be the same thing. What happens to Y as X changes? Notice, I'm not asking how much variance in Y is explained by X when I talk about beta. I'm saying literally, how does Y move as X moves? That's a slope. Sound a lot like covariance? How does X and Y covary together? That's why they're the same. Now, if I want to know the variance in an outcome explained by a predictor, I don't want the X and the Y movement. I just want to know what happens to Y, how much of Y changes based on X. So I have to square beta or square little r. So in simple regression, r equals beta and r squared equals beta squared, which equals the big R squared of the model because we're only working with two things. Again, if you are struggling with this, the only way is to try to reproduce this yourself with your own drawings and your own notation. It will not, if it isn't sticking, it won't stick by watching this again. It will only stick by trying to do.
What about
But
the big
now,
R?
yeah, go ahead.
What about the big R, not squared, just the big R?
You tell me.
It's the unstandardized.
No, don't tell me the name of it. Tell me what it's gonna be equal to in a simple regression. It's a type of correlation coefficient.
Yeah,
So how many things do we have correlating in this whole model, no matter what?
at least two.
Just two. So what does it have to be the same as?
Correlation.
Yep. Don't memorize for these guys, think. Memorizing will get you in trouble. Or mixed up, I guess I would say, not in trouble. Yeah, it's the same. It won't be the same when we get to multiple. But I will say of all the things, Alice, this is the one I don't usually pay attention to. Because in a simple regression, it's the same as Pearson R. And in a multiple regression, it's an unhelpful number. So you can leave it, you can kind of deprioritize it as an important coefficient to understand. Because it becomes unhelpful as soon as it means something different than Pearson R. Yeah.
So all the big R's are about the model.
Correct.
All the betas,
Ooh, beautiful. Yes, let's go.
all the betas are the,
Individual predictors.
yeah, control over any others in the models.
If there are any.
If there are any.
Yeah.
And then all the little R's are just the predictor.
Bivariate relationships.
Yeah,
Yeah,
without anything else.
yeah, good. JJ came up with a nice sort of overarching schema, which is if the R is capitalized, we're talking about a model. You can see that in the model fit table. There's only one place capital R's show up. Model fit. So when we're talking about model fit, or we're talking about big R, we're talking about some feature of the entire model. When that entire model happens to only include one predictor, it looks a hell of a lot correlation. As soon as it doesn't, it looks different. Yeah. Speaking of, when we move from correlation to multiple regression, here we have little r. Here we have another predictor. There's that other predictor. So you have covariance going on all over the place. You have, if I were to annotate this, here is all the covariance between your outcome and X1. And all this is that covariance between your outcome and X2. And then in the middle, you have this covariance that's happening between the outcome and X1 and X2. So how does that then materialize in a regression model? Well, in regression, as JJ said, the betas are always talking about the contributions or the slope or the degree of relationship between a single individual predictor and an outcome. In a multiple regression, there's more than one predictor, so it's asking about the unique contribution of that single predictor. The part where they double up, X1 and X2 don't get credit for that. They have to share. So if I want to know the unique variance in my outcome that's explained by each predictor, literally this is just math. You can think of this as 100% of your outcome. You're just saying what slice of that pie is covered by X2 only. It's B squared, beta squared, sorry, beta squared. But then that part that's starred, do we ignore it? Why not?
Model.
It's still part of the model. What is that part still doing? It's still explaining variance in our outcome using the combination of predictors that we had. It's just not unique. So where's that going to show up?
Big R.
R squared. We don't really care about big R. It doesn't tell us anything. Get it out of your brains. That helps. R squared, the variance in the whole outcome. So now we're talking about, again, 100% of the outcome pie. How much did we cover in the blue? Cool. Questions? Yes, Brady.
But if we do have multiple regression table and a correlation table but we don't have R squared printed out for whatever reason, is there a way to use the betas in your regression table? And
No.
the correlation table to compute R squared?
No, because you can calculate their unique variance that they explain, but you don't actually know how much of what they share in the correlation table is overlapping with Y. Yeah. I'm gonna leave this. It's a sum up table for you in case you want to look at it later. But again, don't use this. Be careful. So from correlation to regression, questions in the check-in. Here is this correlation table that we used. You specify a simple regression model with supervisor cultural competence, predicting identity integration. The R squared for this model would be what? So we have supervisor cultural competence and identity integration. The correlation is 0.34. What's the R squared of the model going to be? So here's the beta. The beta is going to be 0.34, but what's the R squared going to be? It's 0.34 squared. Whatever that is. Someone get a calculator out so we can just have it ready. What?
12%.
Be careful here. Good. If you wrote 12%, Canvas probably marked you automatically wrong. Don't be too bothered by that. You understand conceptually what it means. The R squared itself is 0.12. If you are interpreting that, it's 12% of the variance in identity integration can be explained by supervisor cultural competence. This one. You specify a simple regression model with autonomy supportive leadership predicting identity integration. Okay, boom. Would autonomy supportive leadership be a significant predictor in this model? Yes, no, not enough info.
Yes.
Thanks, Jack. First of all, the R, which is the correlation, is 0.18, and it's significant. What does that mean the beta is going to be in the simple regression? 0.18, also significant. So the answer is yes, you do have enough info. Remember, the relationship between two things. Think about this graph we just did, or this problem we just did here. Correlation and simple regression mathematically are identical. It's just that one is descriptive and one is predictive or inferential. One has a model line, is a model, and the other is just a descriptive of a relationship. But anything that's true about the way two variables correlate will also be true about them in a simple regression. Because all we're doing is examining the relationship between two things. It's saying, are Heather and Hannah sisters? If they're sisters, then if I ask the question, is Heather Hannah's sister? The answer is still yes. You see how it's different? It's the same exact thing. Are they sisters? Or is Hannah sister, or is Heather sisters to Hannah? Yep and yep. Their relationship doesn't change. Same concept.
Jess,
Yep.
I'm thinking the only reason you know that is because it's got the note and the notation there.
Correct.
If
Yep.
you didn't have it, you wouldn't know.
Correct. Yeah, unless it was something crazy, but yeah. In a simple regression with supervisor cultural competence, predicting self-determined motivation, the beta would be 0.30. So first of all, let's find the R. The little r is 0.30. So that means supervisor cultural competence and self-determined motivation are related at 0.30. If I make one the predictor and one the outcome, does how related they are change? No. So true or false? True. Good. In a multiple regression model with supervisor cultural competence and identity integration, predicting self-determined motivation, the beta for identity integration would be 0.06. So that's the little r, but now what's different? Good, which means that's the different analysis, but what does that mean substantially? It means that I'm no longer looking at just this relationship. I'm looking at this relationship when I consider the influence of cultural competence, which means it is not going to be the same thing, okay? The answer is false.
Are you looking at the correlations there? SCC and predicting self-determination?
It says the beta for identity integration would be 0.06. So identity integration is 4, self-determined motivation is 5. So the correlation is 0.06 between those. That won't stay 0.06 when you enter it in a multiple regression. You with me?
Yeah, I was just reading one half the question, not the other.
Oh, cool. This stretching. All right, model fit. These are actually leftover questions. You didn't ask these. All right, fitting and estimating parameters. So just because it's the best doesn't mean it's good. Somebody asked for this. Can we have a slide representing the mathematical and conceptual relationships between the variables listed on the table? I think I have these. I added a tiny bit more formula, but if this is not what you were talking about, just come tell me because it means I don't understand what would be helpful. So just let me know. But here's our model fit table. What are the things that we're really gunning for on this model fit table? That's it. R squared, that's it. Yes, we can put the F in the regression table in our manuscript if we want, but really what we care about is, hey, I care about self-determined motivation. How much variance in that did I explain? How much spread, meaning some people are high, some people are low. How good was I explaining somebody being high or low, predicting somebody being high or low? That's it. Yeah. Except that, yes, except that on a fit level, the of having a p-value that isn't significant is so small because you're comparing it to a model with nothing. And if the p-value, these are going to go together. If the p-value is not significant, what's your R squared going to be? Super low. This whole thing is telling you how good is your model. So it's not you can get an awesome R squared and a non-significant P. Yeah, really quick, because we got a lot left.
When does delta R squared mean more than R squared?
When we're comparing models. Here, we're only looking at a single model. You can't look at change in R squared until you have two different R squareds to compare.
But those things go together.
Yes. Delta R squared is literally R squared of one minus R squared of the other.
Yeah, but as in they're reported together.
Yes. Oh, I don't need this. You don't need this either. You know B and beta. The one thing I do want to show you, B and beta. This is the formula of how you get from B to beta. Not that I want you to know that. All we're doing is putting things in standardized units. I just want you to remember, sometimes I hear people talk about B and beta. They're different things. They're not different things. They're just different units. It's when we standardize with z-scores. Here we go. This is the relationship between optimism and happiness. What's the same about these graphs? The points, the slope, the intercept. What's different about the graphs? Just the axes. Betas are in the units of standard deviation. B's are in the raw units of however you measured X and Y. So all we're doing is if we want to get from raw units to beta, we just have to scale it by the standard deviation of X and the standard deviation of Y. You're not going to have to do that because you get it in your output. But I want us to understand that really the slopes don't change. The relationships don't change. They're just a different unit of reporting. Again, if I measure how tall Amelia is, we're going to measure in different units. But Amelia is not getting any taller or shorter. We just use different systems of measurement.
So conceivably, could you use beta in your equation instead
You could,
of,
but why on earth would you want to?
but you could. it would be,
It would just have no intercept, because the standardized intercept is 0. Yeah, so look, I think I have this later. Yeah, if your equation is standardized, you must enter standardized values of X to predict an outcome. But that would literally mean converting someone's raw score to a Z-score. So it's like, if someone's a 5 in optimism, what's their predicted happiness score? I would have to, if I only had a standardized equation, I would have to convert 5 to a Z-score. How far away is 5 from the mean? I don't want to do that. So I'm always going to use an unstandardized equation for predicting values. Oops. 10-15. Let's take, I just want to show you this. This is what I thought people wanted when they said conceptual and mathematical. It's the same slide as what I've had in the past several multiple regressions. The only change that I added was I added the confidence interval. So you can see how the confidence interval is actually made up of the estimate with error on either side. And I added that standardization of B to beta, but that's really the conceptual and mathematical together. Good. Come back at 10:25 and we'll keep going. But don't be, we got a lot left. Okay. So picking up with multiple regression. This question from the review, if standard error of X were to increase, the t-stat for that predictor would go down and the p-value would go up. So remember, this is our best fixed estimate for the relationship between self-efficacy and desire to lead. This is what R has estimated as the relationship out there in the population based on our data. The question is, how good of a rule is that for everybody in our data set? The standard error gives us essentially the badness of that fit. More standard error or higher standard error means the points deviate further from that slope estimate. So the slope in standardized form, because that's the only way I can draw it. So B equals 0.75, beta equals 0.43, same thing, both the slope, just different languages. How far the points are, that's representing how much error there is in our parameter estimate. So if our standard error goes up, that means more what? More error. More error means what about the model, that slope? It fits what? Worse, which means how confident are we? If we were yay confident in the relationship between self-efficacy and desire to lead here, and all of a sudden it fits worse, what's going to happen to our confidence? It goes down. Our interval gets wider. And what happens to our P? It goes up. For lack of a better term, it gets less significant, even though we're never going to say that. More importantly, it says, hey, the probability of getting this, assuming there's nothing there, gets higher. Because now there's more error in there. So it's true. Is it possible to specify a model that is significant and has a high R squared, but no significant predictors? Remember, R squared is the variance in our outcome that's explained by the linear combination of all our predictors combined. It does not care how much your predictors overlap with each other. It's just, if this is the pie, the pizza of your outcome, how much of the pizza gets eaten by your predictors? It gets explained. Here we have a significant R squared. Here we have a significant R squared. And here we have a significant R squared. But they're very different in terms of how the two purple predictors are contributing. In the first one, both the predictors are contributing unique stuff. That's the orange. In the second one, only this one is contributing uniqueness. And the second one's just giving a tiny little bit. So it's what is going to be really small, beta. How about in the second one? Both the betas are really tiny, tiny, tiny because most of the variance that's getting explained is shared between the two predictors. This is what? Collinearity, multicollinearity or collinearity. That's when you can get a significant R squared and no significant predictors, when you have an extreme case of multicollinearity. Our parameter interpretation. So here's the parameter table that you looked at. Here we have our parameters. Those are really the two parameters that we're interested in, intercepts and slopes. Those are the parameters that are getting estimated by ordinary least squares. Now we're gonna go through the questions in the check-in that asked about this. Not too bad on this one. The predicted leader identity score for someone with 2 years of management, a 6 in core self-evaluation, a 5 in experienced microaggression, and a 9 in positive racial identity is what? First of all, what model should you use? For 2 reasons. Yeah, good. What model though? Model 2. Why model 2?
Because that has microaggressions, the other one doesn't.
Yeah, simple reason is I gave you the data for all the predictors in model 2. So use model 2. The other reason is model 2 explains significantly more variance than model 1. So what's the next step? This is important. If you're given a regression table, if you're given a parameter table, this is a model. This is a model in coefficient table language. What do we have to do if we want to predict a score? Translate it into equation language. So how do I do that? I have to use the set of parameters. Well, what type of input do I have? Raw, unstandardized. So what type of equation do I want to use? Raw, unstandardized. I'm literally just going to go through and I'm going to say y equals 0.61 plus 0.0072 plus 0.836 plus 0.485 minus 0.129. And then plug that into your calculator. Like I said, if you have not updated your phone so that you can keep all the terms on it, or you're not using well, you can't use your phone on the test anyway. So if your calculator, keep all the terms together so you don't lose it. Yeah.
What if you put 0.00 for that first slope? You know, if you're rounding.
This one? Good. So the general APA rule is you round to the first significant digit if the first digit doesn't happen in 2. So if it's 2 digits, and even if you did, it would be what? 0.1. So you could round it to 0.01 and that would be fine. Or you could leave it as 0.007, but 0.01 would actually be the more appropriate in this case. But if something rounds to 0.00, we usually include the next digit or as many zeros until the first significant digit, we call it. Yeah.
Is it not standard 2 scientific notation?
Not in an equation. Yeah. What was the actual answer? Anyone know? You don't have your check-ins up to know how you did? That seems weird. 6.92. Great. 6.92 is their predicted leader identity. David has 1 year of managerial experience. Krista has 10 years. Assuming they have the same scores in core self-evaluations, microaggressions, and positive racial ID, what will the difference in their leader identity scores be? Now, we could go back to the full equation. We could. All we have to do is assume that they have the same scores in these. Who cares what they are? Just keep them the way they are. The only difference is David has 1 year and Krista has 10. So you could do out the whole equation for David and the whole equation for Krista and see what the difference is. But you don't have to, because this coefficient is the change we would see for a 1 unit increase, meaning 1 more year managing. We would expect leader identity to go up 0.007 as long as 2 people have the same scores here. Because if they don't, it's going to change the whole equation. Now, what a lot of you did then was multiply 10 by 0.007. That's wrong, because how many more years of experience does Krista have than David? 9 more years. If I have a year, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 9 times 0.007.
I think I did both. I think I did both equations and then subtracted one from the other, but I still got it wrong.
Well, that's probably a math issue, but it should work that way. I have questions about that. Interpret in context the unstandardized regression coefficient for core self-evaluations in model 2. So a lot of you, look at that percentage. This is the lowest question. Any idea why? Yeah. Yeah. A lot of you said, oh, first of all, 0.83 and 0.57. That's what? That's the relationship between core self-evaluations and leader identity in this model. It's the slope between core self-evaluations and leader identity in this model. But what makes this model special is that it's taking into account years of management experience, microaggressions, and positive racial identity. So you can't just say, for every 1 more point increase in core self-evaluations, we'd expect leader identity to go up by 0.83 points, because that's not true. That would be a simple regression interpretation. If you don't say holding these things constant, it's not, because as soon as we don't think about why. Here's the whole equation. There's the whole equation. If someone has a 5 or someone has a 6, that's a 1 unit increase. So for a 1 unit increase, this whole thing's gonna change by 0.007, meaning y is gonna go up by 0.007. But not if I start plugging other stuff in here. If I start plugging other stuff in here, then this whole y is gonna change. So it has to be while holding these 3 constant. Then, if these are held constant, meaning if these are not changed, if no matter what, let's say it's a 3, a 3, a 2, a 2, a 1, a 1, then the only difference between these two equations here is what? It's this. It's the 1 unit increase in core self-evaluations, which means that the only mathematical difference is going to be 1 times 0.007. Yeah.
It just currently your difference in the years again versus the first evaluation. That's the mistake timing.
Huh?
It's currently the differences in years.
Sorry. Thank you. It doesn't matter.
No, I
Same
know.
concept. Yeah. Cool. Do we get it? Yes. No matter what, if we hold, same thing happens here. So if we want to do it with your core management or any of these, if we are looking at a 1 point difference here, but everything else about the model is held constant, then the only difference is going to be a change of 1 times 0.83 is a 0.83 difference. Yeah. Yeah.
So how would you interpret this?
For a 1 unstandardized or 1 point, if I know how it's measured, I'm going to say that. So if it were years managing, I'd say for 1 more year of management experience. But in this case, I might say for a 1 point increase in core self-evaluation, a 1 point scale increase in core self-evaluation, I'd predict a 0.83 point increase in leader identity, holding years managing, microaggressions, and positive racial ID constant.
Is it just to say holding all other variables constant?
Yes, it is not to say accounting for all other variables, because accounting for all other variables does not say anything about what I put in for those values. Accounting for is fine in storytelling. It's not fine in interpretation. Lex.
So we just always have to add that so at the end.
But why? I don't want you to be, because Jess told you always have to add it. Why? This is not the if I were to run a correlation table with, or let's look at core self-evaluations. If I were to run core self-evaluations on leader identity, that slope would not be 0.83. 0.83 is only the parameter that got estimated once those other things were taken into account. That's why. Does that make sense? Because sometimes when we take other things into account, the relationships change. I'm gonna keep going because we're really tight on time. What's the equation of the regression line for your strongest model? The only reason that we're 68% on this, there's one reason. When you get to positive racial ID, I didn't care if you did the names of it, years managing or X, I don't care. This is not how you write an equation. It's not plus or minus. It's just, oh, that's messy. It's just minus. Yeah. That's the only reason that we struggled with that one. Dummy coding. Dummy coding. Not too bad, actually. Overall, across all the dummy coding questions, average was an 83%. This is the example from that check-in. Social psychologists conducted a study to predict happiness based on social support and employment status. Employment status is dummy coded with 3 levels: unemployed, employed part-time, employed full-time. Unemployed serves as the reference group. After collecting the data, she centered her data and derived the following unstandardized regression equation. Quick question here, because this came up in the check-in. It's not a client. In the first check-in, can you explain which parameters are fixed or not fixed? How many this is the full equation. Yes, the intercept changes when we consider this last part of it, but this is the full equation for the whole model. How many intercepts does this full equation have? 1. How many slopes does it have? 1. They're both fixed. It's not a random model. This part of the equation here happens to change the starting point, but we're not actually varying the estimated parameter. It's part of the equation in the model. So everything we're doing now are fixed models. Again, I didn't teach you about random models because we're doing them. I just taught you about random models so that when you see it out there in more advanced stats, you're not, what's a random model? But in here, we're just fixed models. Oops, keep. All right, so here we are. Here is our dummy coding scheme. Unemployed 0, 0, part-time 1, 0, full-time 0, 1. The predicted happiness score for someone who's unemployed with average social support is what? So we have 4.52 plus 0.45. We're centering, so that's going to be 0, and unemployed is the reference group. So what goes away? Everything but the intercept, 4.52. Because this asks about averages, I'm going to pause us for a second actually and skip to my centering section so we can get that down and then come back. By the way, if you download this PowerPoint, it's got headers, sections, do you know what I mean? So it's centering, blah, blah, blah. Except they don't show up here. That's really helpful. Thank you. Here we go, centering. All right. Here's raw data. Raw data, social support predicting self-esteem, just plain old raw data, nothing special. Here is our graphed simple regression. We've got a slope, P1. We've got an intercept. What is that intercept? What are the coordinates of that intercept? Roughly 0. The x is at 0. Everyone familiar with how to write coordinates of a point? X, comma, y. How we write a point. So this coordinate here, the x is at 0. What's the y at? 1.8? I don't know. We're just eyeballing it. Good. We good with that? Great. If we ask for the parameter table that goes with this, we get this. And in fact, it was 1.94. We were just eyeballing it. And this is the predicted value of y when x equals 0. If you want to think of it more broadly so you don't get mixed up, you can think about it as the predicted value of y when the x is located at this y-axis, at the x equals 0 position. It's not the predicted value of y when somebody responds 0 in your survey. It's a predicted score of y when the data point x is here. So here's 0, and we could estimate whatever that y is. That's what that means. So here we did it with our eyes. 0, 1.8. It's actually 0, 1.94. Cool. Now, if we want to, we can mean center our predictors. What we do is we take all of our predictors and we subtract the mean. I just rounded to make this 4. And we subtract the mean of the x value. And watch what happens. I'm going to do that again. Everything just moves over. Now, what's this point? It's still x0 because we're at the origin, but now what's the y roughly? 4 point something, 4 point something. And in fact, it's 4.07. So it's not, we haven't changed the positionality of the intercept. The intercept is always the value of y when x is here at the y-axis. The only difference is, did we leave the axes where they are, or did we subtract the mean from every number so it moves over? Yeah.
Can we say that we basically put it in context of the mean?
Yes. That's basically what centering is doing. And all it does is change. The reason it's tricky is that this is the ultimate interpretation. It's the value of y when x is average, but it's still the value of y. It's still the point where the line crosses the y-axis. It's still at this line. It's just that now we've shifted everything over left. So in this 0 that was here is now way over there, and this is the average of x. So now the true value is average x and then y-intercept. So this is the centered, and the uncentered is 0 y-intercept, true 0. Look, nothing changes about the relationship. Nothing changes about the slope. The only thing that changes are 0, 1.94, 0, 4.07. Questions about that? Yes.
Can you create the regression line with the centered data? Is it just the same, you just switch the numbers?
Switch the what?
So you can create a regression
Yep.
equation with centered data?
Yep, that's what you've been doing in your DAs. When you center all your X's first, think about so in your original raw data, you have a Y column and you have an X column. Once you center, then you have a centered X column. What you're really running is that regression. So now all the values are just weird, wacky numbers above and below the mean. They're all relative to the mean of X. So if someone is a 0 with this value, what does that actually mean? Careful, think about that. I want everyone to think about that. Yes, if you have all your original data and you center it and someone ends up a 0, what does that actually mean they put in the survey? How do we get from X to X centered?
Would they be the mean?
They'd be the mean. Because X, here's all their values. To center, we subtract X bar from all of them, and you get new centered values. Well, the only way to get a 0 is if you started off as X bar to begin with, 4.07 specifically. So we see how when you're at 0 here, you're not really 0, you're really the average. Now, this column of data is expressing whatever you put down in your scale, not by your raw number, but by how far away you are from the mean. So by saying you are 0, as in 0 away from the mean, you are the mean, okay? Doesn't change the relationship, just changes the intercept. Now, if I want to use a centered equation, so here's a centered equation. If I want to know the predicted self-esteem score for somebody who is average, how do I get, remember, how do I get a centered score of average? What do you have to be? What do you have to be? If my raw score is the actual mean, then what is my centered score going to be? 0. If you're in my data set and your score is 4.07 and I subtract the mean from you to get centered values, your new centered score is a 0. And that's what I entered into the regression model, which means I'm just plugging in a 0 here. And all you're left with is that intercept. What if you want to know the predicted self-esteem score for someone with a social support score of 5? Can I do this? Why not? And don't tell me because it's centered.
You have to subtract the mean.
But why? I didn't run social support on self-esteem raw. What did I really run? I run the centered version of your social support scores. I run everybody's centered scores onto their self-esteem scores. So I can't plug in a score in a unit I didn't use. So I have to express that 5 based on where they are relative to the mean. So I have to take 5, subtract the mean, and then I can plug it in. So the moral of the story, I have it here. If your equation is centered, you must enter centered values of X to predict an outcome. If you have no choice, here's your centered equation, or here the values were centered prior to analysis and that's all you have to center them. If you have your choice, use uncentered because you don't have to center. Now let's go back to dummy. So now we don't have to do all that to answer these. The predicted happiness score for someone who is unemployed, as in 0, 0, their scheme is 0, 0, is just going to be 4.52. Why? Because what are we plugging in here?
How do you know using center data there?
Because it's in the prompt. Now, I'm plugging in 0.45, I'm plugging in her X value, but am I plugging in her raw X value or her centered X value? I'm plugging in her centered X value here. If somebody is average, what's their centered X value? 0. Because how do I get from X to X centered? I take whatever you are and I subtract the mean. And that's how I get it. So if you are average and I subtract the average, I get 0. The predicted happiness score for someone employed part-time with average social support. So 4.52 plus 0.45 average, that's your centered average, x dot c. Part-time plus 0.101 plus 0.300. I get what? 4.62. And if you're full-time with average support, this goes away, and I get 4.82. The slope between social support and happiness for unemployed individuals is blank. The slope between social support and happiness for part-time or for full-time. And then a lot of people ask this question, when will the slope change? I don't need to tell you, you can figure it out. Look at the full equation. What are the two values that can get plugged in for this variable? 1 or 0? How about this one?
0.
Sure, let's make it exciting. 0 or 1. Great. If I put in a 0 here, what's gonna happen to the whole thing? It disappears. If I put in a 1, what happens to it? Becomes a number. What am I gonna do with a number? I'm gonna add it to what? The other number, the intercept. Does anything here mess with this? No. You guys know the idea of like terms? If you have 2x and 2x, you can add them together and get 4x. If you have 3z and 2z, you can add them together and get 5z. You can't add 2x and 2z and get 4 giraffes. I don't know. So same as here. You have 0.45 social support. Do you have any other social support anywhere? No. That is the slope that OLS has estimated, taking into account those other things. It says, hey, you guys are full-time, you guys are part-time, and you guys are unemployed. You probably might have different relationships, but you're asking me for one model. So I'm gonna pick the model, I'm putting all your dots on one graph, and I'm estimating the best single slope for all of you, and it's 0.45. So guess what? The answer is, in regular regression, it's never gonna change. 0.45, 0.45, 0.45, the end, okay? What is gonna change? The intercept. Good, so we can do that. If we want to simplify, remember, these can become eliminated or they can become 1. If they can become 1, they're gonna change the starting place. They're gonna change the intercept. So the simplified regression equation for part-time workers would be y equals 4.52 plus 0.45 social support. Fixed parameters for the whole model, no matter what, they don't change. Plus 0.101 plus 0.300. So what can we do? We can get rid of this, okay? Then we can simplify again, y equals 4.52 plus 0.45 social support plus 0.10. Is this simplified? That's why we're at 52%. You can't leave your equation like this. What are the two components of a model? Intercept, slope. Do we have two things here? No. We have an intercept and then another little piece of its intercept and then a slope. So we have to finish it. 4.62 plus 0.45 social support. Yes, Emily.
Is there two continuous variables in the model?
Same thing, be the same for each of those. So if it's y equals 4.52 plus 0.45 social support plus 0.23 happiness plus 0.10 part-time plus 0. This is the slope between social support and whatever, and happiness. Oh, it should be happiness. Let's do optimism. Between social support and happiness, considering your employment status and your optimism. And this optimism slope would be the slope between optimism and happiness, considering your social support and your status. Yep.
This sounds silly to say a lot, but a multiple regression is basically a model that is estimating multiple slopes.
Yes, but not necessarily, because how many slopes are estimated? I wouldn't say multiple slopes. How many slopes are really estimated here? It's really just one slope. Multiple it's estimating the unique contribution of multiple predictors while accounting for each other.
Yeah, yeah.
It's kind of saying, how much does any one of these things matter if we also take into account the other thing? So it's kind of the idea of saying, here's a negative example. Let's say you study a lot. That should impact your test scores. Well, what if we take into account how much you slept? Then does studying matter quite as much? No, maybe not. Because if you didn't sleep at all, then it doesn't matter if you studied 100 hours because you're not awake for the exam. So that's what I mean by it is going to estimate the slope between a single predictor and an outcome in the context of the other predictors. That's the benefit of multiple regression. That's why we do multiple regression and not a bunch of single regressions. Because out there, it's not just you studied, it's you studied and you slept a certain amount and you either fought in the morning with somebody or you didn't. There was traffic or there wasn't. You ate well or you didn't. You feel confident or you don't. There's all these other factors, and all of those factors influence how strongly any other factor predicts the outcome. So when we put them together, we're allowing the effect of each of them to be considered in addition to the one, whatever we're interested in. Yeah.
We're going to, when reporting or visualizing our model, when we just have one continuous variable, we've been able to see.
You can graph it.
Would it be planar? How does?
Yeah.
Addition of a variable.
What happens? So if you have a model this, you can graph it. Because we've got one slope and we've got just 3 different intercepts. Look, yay, I did it. Here's what it would look like. So you can literally plug in Democrat, Republican, and Independent, and you have 3 separate simple regression equations, and you can graph them. But what happens if you have another continuous predictor? What if it's happiness, or what if it's the vote predicted from voting history plus party plus age plus something else? Instead of X and Y, you have X, you have Y, but you also have a bunch of other axes. It's a 3-dimensional graph. You can't draw it, okay? You can't visualize it or draw it, which is why the betas become extra helpful, because I can draw this one unique relationship. I just have to remember that that's the relationship considering these other things are in play. Just don't forget that part. The one thing that I wanted to show you here was this question. If one coefficient of a dummy-coded variable is significant and the other is not, can we say that a variable is a significant predictor of the outcome? So here is the example of political party predicting the vote, considering somebody's voting history. So M, to your question, it's if I just use political party, it would be, what party are you registered with? I'm an independent. Your vote is this. Well, no, we're saying I want to know your voting history too, and then I want to also know your political party. And now when I know those 2 things, I can make a more accurate prediction. So the question is, when we look at our 2 predictors, look at these results. For storytelling, where do my eyes go? Beta and P. That's where my eyes go for storytelling. So the reference group was Democrat, and what do we find? We find that there is a difference in the vote between Democrats and independents. When we move up in D2, so that's from 0 to 1, because those are only options. So when we move from a Democrat to an independent, they become less to vote, significantly. hence the p-value. But when we look at Democrats versus Republicans, there's no change in the vote. It's not significantly different. Yes, the beta is negative 0.13, but out there in the population, we cannot infer that there's a significant difference. So then the question becomes, one is significant, one level's not. Can we say that political party, which is our construct, is a significant predictor of the outcome? Yes. You cannot ever divorce levels of a categorical variable. Just because you have 3 levels, Republican, Democrat, and Independent, you have concluded that there is a significant difference somewhere amongst the political parties. Not everywhere, but somewhere, which means political party is a significant contribution to the vote. Kayla.
So I know that we can't divorce them when we're talking about the significance of the predictor, but like, what about when we're discussing it, can we ever discuss them?
Separately? Yes, absolutely. So I would say something, this, political party is a significant predictor of the vote when considering voting history. Don't forget that part. However, more specifically, independents were significantly less to vote than Democrats, beta P, but there was no difference in the vote between Democrats and Republicans, beta P. Yep, good. Construct, individual level variables. Yeah.
So I understood everything you just said, but I think the confusing part for me is with interpreting the reference code that we put in variables, because it's not there as visually.
Yeah.
Can you just repeat the part where you interpreted the Democrats against the other?
Yeah, so remember that a Democrat is a 0, oops. The Democrat is putting a 0 against this coefficient and a 0 against that coefficient. So it's those two things completely disappear from the equation. So you can't actually ever say anything about the reference group on its own in terms of significance. Dummy codes are always moves from 0 to 1, as in 1 unit increases. So a 1 unit increase in D1 is 0 to 1. So it's a 1 unit increase in D1 is going from 0, 0 to 1, 0. That's D1. And a D2 increase is going from 0, 0 to 0, 1, which has that's the 1 unit, but our 1 unit mathematically has symbolic meaning because we've coded it that way. We've coded it that a 1 here actually isn't just number 1, it's you're an independent. That makes sense? But it's always in reference to it's always compared to or moving from the reference group to this group. We did this. So you can generate simplified equations for each level, but don't forget you have to combine terms. You can't have 2 numbers. You can't have 2 intercepts or 2 pieces of intercept. 1 intercept, 1 slope makes a full equation. So here we go. Why do we fit 1 regression equation instead of separate regression equations? There's one answer to this. It's got 2 words, research question. If your research question is, what's the difference between Democrats, Republicans, and independents? And they'll vote, cool, run 3 separate regressions or run an ANOVA. But that's not what we're asking. We're asking, how does the vote and political party influence, or voting history and political party influence the vote? We're just manipulating a categorical variable to fit it into our regression model. It's not our focal question. Yeah.
Could you give an example of how to interpret the beta for a categorical variable?
Yeah. Same exact way, it just doesn't hold a lot of meaning. So you'd say as you move from Democrat to independent, then the vote is going to go down by 0.47 standard deviations. No different. It's just not a very helpful. It just doesn't have a lay utility.
Okay.
Yeah. Because it's categorical, they're treated a little bit differently. Yeah.
It's called the DA, but when you draw a figure.
I'm about to do the DA now.
Okay.
So some questions about the DA. This was post-grad success being predicted by income, literacy, and high school graduation status. So reference group was didn't graduate, on time, and later. There's the coding scheme for that. First thing is, let's look at our correlation table. What do we notice? Well, income and illiteracy are negatively correlated. That makes sense. Illiteracy and success are negatively correlated and income and success are positively correlated. What we don't have in here, which is a good thing to think about, is we don't have what? We don't have high school graduation. We don't have high school graduation, which is related to which of these things? Probably all of them, but probably super related to what? Illiteracy. Yes, think about that. It's gonna come up in a second. All right, so here we have model one. Model one explains 53% of the variance. Model two also explains 53% of the variance in post-high school success. That difference, not significant. So now let's look at the actual model coefficients. So here we have model one that's got income and high school graduation status, and model two has income, high school graduation status, and we added in illiteracy. And let's just note for storytelling purposes, I know this isn't the better model, but it's not significant. And what happened to these other predictors? Very slightly. Tell me the story of this. What happened? Why did adding in illiteracy after we had income and high school graduation status? Why was illiteracy not significant? And why did all three of those other ones go down, but only by a teeny tiny bit? Yeah.
They're a little bit linear, so it takes that out of their individual data.
Good. So they had these individual contributions in model one, and some of it was collinear. You can see it in this tolerance score. Some of it is collinear with illiteracy. As in lay terms, it's redundant. If you know how much money somebody makes, and you know when they graduated high school, adding their literacy level doesn't add significant predictive value above those other things, because illiteracy is so closely related to those other things. Now, this is also the danger of regression. Is that true for everybody? No. You can absolutely not go to school and be completely literate. So it's not always true. It's not a one. That's why the tolerance isn't 0. It's why it's 0.5. It's got some unique contribution, but once you include all this other stuff, as a rule, as a fixed parameter, it's not unique enough. Yeah.
It's also something that we kind of got a hint of in the graphs too.
Yep, exactly. You should be able to start seeing that in the data. Yep. So we have our other variable here, and here are p-values. So D1 is the difference between somebody who didn't graduate and somebody who what? Graduated on time. So how do we interpret that parameter? Considering their income. Yeah, good. So when we consider people's income, people who graduated on time are significantly more successful than people who didn't graduate at all. More specifically, if you have two people who make the same amount of money, the person who graduated on time is predicted to have 2.29 points higher success score than the person who didn't graduate at all, assuming their income is the same. That's the holding constant. Now, we have the same situation here where, is there a difference between people who didn't graduate and people who graduated late?
Is it fair to say we're seeing an effect in the sample, but there's not enough statistical evidence to infer a relationship?
No, because you don't care about your sample. Now, you could in your in your discussion, I'm noticing the same thing, which is that's not significant, but that beta is pretty substantial, let's call it, of note. Usually you don't get a beta of 0.23 and a non-significant p-value. Why is it happening? Because look at your error, right? Your error relative to your coefficient. So yeah, it would be totally appropriate in your discussion to be, maybe we're underpowered, maybe right, all sorts of reasons. So it's a good thing to notice. But for the sake of interpreting this model, no, out there, there's not a relationship. Though I will say, look at this confidence interval. Ooh, now I'm gonna go back to, look at that. What is that? Here's your confidence interval. Where's 0 located in your confidence interval? Like here. So yeah, Allie, I would say that's probably your result section to be, if you look at your confidence interval, the probability of it actually being 0 is so small given your confidence interval range, that we might, in an alternative sample, infer an effect. Yes. But it is not significant. Yeah, that's actually a better statistical interpretation here. That's taking all the pieces into account. If this were not significant and this were smaller, if there were not other pieces or other clues, we could say there's no difference between students who didn't graduate and students who graduated late. And then our advice would be, just make sure what? Make sure, not just make sure you graduate, make sure you graduate on time. But in this case, I think you're probably Allie, which is, it seems to me from all the pieces of the pie, that it's more that graduating late and graduating on time are both better than not graduating at all. If you take all the kind of combined pieces together. What are two pieces of evidence that you can use to tell me that high school graduation is significant?
The delta R squared.
So one of them is we don't have it, or we do if you did income first, predicting success, and then you did income plus high school grad, as in D1 plus D2, then yes, the best way is to give the models the R squared. Totally, or you could just run a simple regression with D1 plus D2 and give the R squared. What's the difference between these? They're very different.
Represents the change specifically.
But what's the difference in these models? These models aren't the same. What? No?
One of them hold against one income.
Yeah. Once saying know your income. Then how much does high school graduation matter? The other is saying, I don't know anything except whether you graduated from high school on time, late, or not at all. How much does that matter? So the one danger here versus this is you could end up with a simple regression that's significant and then a multiple that's not. You gotta be careful. Because a simple regression is just a correlation. It's one predictor, one outcome. Ignoring the rest of the world. As if there are no other factors that contribute to success. Yeah, quick, because I want to keep us.
I technically did it this way, but
Yeah.
only because I, when I was doing the regression, I kind of parsed it out individually. But I just kind of ignored the first one that was only high school, because the research question.
Yeah, it depends on the research question. That's exactly right. Yeah, what's the other way I could tell you it's significant? I could give you the individual betas and we found a significant difference between not graduating and graduating on time while accounting for income. Therefore, clearly high school timing of graduation matters to some degree. Either one is fine, but you have to be careful. Big picture, you have to be really careful about whether you're evaluating the contribution of a predictor, accounting for anything else that's going on around you, or in isolation. Sometimes we're mixing those up because those change things. And then the last question, what's the slope of the line? According to the best model, what's the slope of the line for graduated on time? What is the slope for did not graduate? Are they the same or different? Explain why or why not. Well, to say between income. Yeah. What's the slope? Really the question should say, what's the slope of the line between income? What's the slope of the line? First of all, what is the line sloping? What on what? Success and income.
Yeah.
What's the slope? You can either say this really crazy thing, or you can say beta equals 0.28, which is probably what I would do. What's the slope for didn't graduate? 0.28. What's the slope for graduated on time? 0.28. What's the slope for graduated late? 0.28. What's going to be different? Intercepts. Same slope. Yep.
One way to interpret it, so the predicted success score of the individual increases by 0.7 for every additional $1,000 of income.
Can I hear that again?
Yes.
Yeah, Emily this is a ridiculously small number that's uninterpretable. So instead of saying a 1 unit increase, why don't I say $1,000 increase? That's why it's so small, because I got a raise, it was $1. If we're minimum wage, yes. But usually if we're talking about yearly income, we're not talking about $1, because I think it was measured yearly income, not dollar per hour. So the idea is 1 unit increase in income of $1 is not super meaningful. So that's smart. I just multiplied. I said, what about for $1,000 income? How much would I expect that to go up? Much more interpretable.
For 10,000, it's a 7-point increase, but the scale is 0 to 10 or 1 to 10.
Yeah. Yeah, good, awesome. By the way, when you have 3 lines of this and you're trying to figure out whether they're different that's the p-values of your coefficients. So if this is did not graduate and this is graduated late, that difference is the 1 unit difference from didn't graduate to graduated late. And the P tells you whether that difference is significant or not. I'm gonna make you do this on your own. We've done enough of it that can now help you do this one. Model 1, just the questions. Model 1 predicts performance. This is a question from the review. Model 2 predicts performance from motivation and ability. Model comparison shows that the delta R squared is 0.19 and P less than 0.001. However, this is insufficient to determine whether the beta for ability will be significant in model 2. I was so sad. I thought I added salt enough times. What's the only difference between model 1 and model 2? If I have a pot of soup and I add salt and the soup gets better, who is responsible for making the soup better? Salt. So the only thing we added here is ability, and it made the model significantly better, which means ability is a significant, unique predicting addition to that model. False, you have enough information. It's whenever I put the answer don't have enough information, if you're not, you know what this is though? This is just a really self-efficacy barometer. I feel like if you put do not have enough information, that's the safe answer. Trust yourself, you know that. You know that. This one was decent, 70% for each of the following model pairs, sort them into nested and not nested. So this is comparing models. So here we have, this was the one that was, so we have A, B, and A, F, C. How do we get from A and B to A, F, C? We took away B and added, let's just use these symbols. So we took away B, I'll use an X. Took away B and added F and C. If we take away something and add something, they're not nested. How did we get from R to KRF? Added K, added F. Cool? Yeah, nested. How do we get from, I always start with the smaller model, it's easier. How do we get from Z and M to Z, Q, and M? Just add Q, nested. How do we get from A and B to A, B, C? Just add C, nested. How do we get from RFT to RFQM? Take out T, add Q and M, not nested. If you look at this one, here's R, F, and T, and here's R, F, Q, M. To be nested, all of this has to be somewhere in the model above. It's not. I can't find RFNT in this higher order model, not nested. Questions about nesting? Control variables, we talked about this really briefly. What's the most important thing to understand? Two key points about control variable. One, they're just variables. They're just predictors. What's the second key point about control variables? Put them in first. Don't just put them in first, run a model with just them as predictors. I don't care what else you want to study. If there is a control variable, it goes first. Cool. That's it. That's all you need to know about controls. All right, we did centering. Ready for the last thing? Can you do me a favor? Would you call Luciana and tell her that I'm finishing and that I will be there as soon as I'm done? Thank you. Assumptions. I'm not going to go over this slide because this is a reference slide for you. But I am going to go over each of them quickly. Linearity. If we are using a linear model, then there needs to be a linear relationship between our predictors and our outcome. Not our dummy coded, not our categorical, just our continuous. Is little r enough to know linearity?
No.
If Pearson R is 0.78, can I be they're linearly related? No. Because what does Pearson R assume? Don't forget, these are assumptions. These are things that are analyses or assumptions aren't things we assume. This is a really important decentering activity. A lot of times we think about assumptions as our assumptions. No, we are not assuming that. The analyses we're running are assuming that. So R, Pearson R, and its way it works is assuming the variables are linearly related. So if it looks this, the points look this, or the points look this, or the points look this, what is R still assuming? Linear relationship. So what's it gonna do? It's gonna give me the best correlation coefficient for the dots. Yay? I don't know. Probably nothing here. Maybe a little bit. So no, the only real way to check linearity is to visualize your data with a scatter plot. That's it. This one, we actually did much better on this than last year. They're not all. I'm not trashing you when I say that. You aren't the only person in the class. Okay, it's good. It means the instruction is better. It's a mark of good of teaching. Yeah, it's a mark of your TAing. You can pat yourself on the back. We did great except for the ones that we haven't covered a lot, which makes sense. Univariate and multivariate normality. However, you could have thought your way to these, and instead what I saw was people going, oh, I haven't seen that word before 100 times, so I must not know it. Don't do that. All right, so linearity, easy. Yes? How do we check linearity? Good. Oops. How do we check homoscedasticity? Residual plots and Bruch-Pagans. How about multicollinearity? VIF intolerance. We've talked about all those. Cool. So now we're left with multivariate and univariate normality. And we're, oh goodness gracious, what are these differences? I don't possibly know. Let's think our way through them before I actually show you. What does una mean versus multi? One. So one variable normality, multi-variable normality. How would you check whether one variable is normal? Histogram, skew, kurtosis. You do it every time you do a DA. Guess what? What?
Shapiro-Wilk or something?
Yeah, you could add Shapiro-Wilks on here if you wanted to the univariate normality. Yep. So again, I just want us to one time, sometimes I get nervous in this class because I work really hard to break things down into digestible, understandable ways, but sometimes I worry that that leaves you not thinking through things when it's not immediately something you've seen. So you have the skills to answer questions you have not seen, but you have to not panic and think your way through them. So let's look at them. Here's the answer. So there are two kinds of normality. One is univariate, one variable. One is multivariate. Okay, that's more than one variable. Whenever we're looking at a univariate normality, we're looking at one variable. We can check out a histogram of it. We can look at skew and kurtosis. But do you remember from ANOVA what the actual normality assumption is? It's that what is normally distributed? The model residuals. So when you have 5 things in the model, it's not about checking each thing. Is the error of the model normally distributed? Check it in one shot. We did it through ANOVA. How do we do that? You've seen these before. We did these in ANOVA too. QQ plots. What do they plot? They plot sample quartiles. What is that? Observed data. Theoretical quartiles. So made up, but theoretically what? No. If we're testing normality, perfectly normal. It's taking your whole model and it's saying, this is what the error would look if it were perfectly normal. This is what the error of your model actually looks like. The more your points follow that line, the more multivariate normal your data are. Sometimes we see points that go this, not very normal. Sometimes we see a point all off in its own here. That's a what? Outlier. If we want to test this with an actual statistical test, to Alice's point, if we want univariate, we can run a Shapiro-Wilks. If we want multivariate, we can run a Mardia test or a Hunt-Zerkler. We've run Hunt-Zerklers. This is all in the grid, by the way. I just wanted to differentiate them. Cool? Yeah.
For multivariate normality, do the predictors have to?
Not the individual predictors, the whole model. Yeah. It's a check. I will check univariate normality visually So this is my general standard when I'm writing a manuscript. I will always visualize every component of my data to make sure that none of my variables are wonky. But then I will usually report multivariate normality because what I'm interested in is the assumption of the model that I'm actually specifying. Why would I check normality of a predictor I decide not to use? Doesn't matter. Same reason why you check assumptions, not just at the very beginning, when you open your data set, but you actually end up checking them on the model you run. Because that's where R is assuming, that's where OLS is assuming all these things about your data. Multicollinearity, I feel like we're relatively solid high level on the idea that if we put two predictors in a model that are too similar, they're going to really lay language mess with the model. Essentially what happens is the outcome, the R has a hard time figuring out who gets credit. That's the really easy way to think about it. If I predict your shoe size from your height, but I predict it in feet and in feet or inches and in centimeters. Well, which one's a stronger predictor? Feet or inches or centimeters? Who gets credit? I don't know. And that can mess with our estimation. That's sometimes where you get betas above 1. Some people are like, I can get a beta above 1. Yeah, because ours, I don't know. F it. I'm going to give all of it to inches. It's not a good estimate. It's not estimating well. That's why we don't want them in the model. So how do we check it? Well, we can eyeball clues. Remember red dinging signals in the correlation table. But where we really check it is where? VIF and which one do I have more? I like tolerance better. Because what I really want to know is, are each of my, I think about your model is going into battle. Are each of my individual predictors strong enough on their own to go into battle? Or are they too influenced by the other predictors? I need them to be tolerant to withstand on their own and contribute something on their own. They can't lean on their other predictor friends. And so I want a tolerance that is higher rather than lower, because if my tolerance is 1, that literally means all of me can't be explained by any of the other predictors. If my tolerance is 0.5, it means 50% of me can be explained by the other predictors. And if my tolerance is 0.1, that means 90% of me is being explained by all the other predictors. I don't have anything to give on my own in battle. Don't put me in the model. Or choose between me and my predictor friend. Which one of us is going in? Because don't put both of us in, it's useless. Pick one. So we're looking for, remember, if we have 3 predictors, so here we have supervisor, conditions, and tasks, we're going to create a tolerance model where one of our predictors is being predicted by the other 2. We're going to get an R squared for that. That's how much variance in this predictor is explained by these 2. What part of this green circle is supervisor supports tolerance? The not shaded part. It's the part that it can contribute on its own, not the part that's explained by the other predictors. So all we do to get the tolerance is it's 1 minus the R squared, really more specifically, it's 1 minus the R squared of the tolerance model. Not your main predictor outcome model, but underneath the hood, it's 1 minus the amount of variance that the other predictors can explain. Somebody asked this question, I don't know where it was. It was, are we looking for a binary threshold? No. Predictors are usually related to each other. They're usually collinear. Now, the degree to which that collinearity is going to be a problem, you don't know, because you don't know what else you're throwing in the model. Sometimes it's no problem. Sometimes it's a big problem. So a big red giant signal that it's a problem is if you get a tolerance that's less than 0.2. But I'll be really honest, that if you're dealing with a tolerance that's less than 0.2, you've got 2 constructs that you should already know are pretty damn similar. Usually, when multicollinearity becomes something to use for an explanation, the tolerances aren't really that low. Supervisor support and colleague support, they're not the same, but it turns out you don't need both in that circumstance. It was, our tolerance was 0.6 or 0.5 or something. It's just when the tolerances and the correlations change above anything that's really high is when you start to go, I wonder. So no, it's not binary, but the tolerance and your correlation table are great clues to figure out why, from a storytelling perspective, why certain predictors might have become or not become significant or not when you change models. If things are too related, or even just related a lot, and you add them both into the model, you don't need both. It doesn't make them the same thing. It just means, hey, once you take into account how much you exercise, then actually it matters less what you eat. It's just how the world works. Some things matter more than others, and some things contribute the same. Yep.
With that in mind, when I was doing the DA, I was looking at what you had covered before in terms of the literacy versus high school graduation. I looked at the correlation table, I looked at the VIF, and the correlation was not that high, and the VIF was 0.5, so I didn't even bother mentioning it. I just said there was no multicollinearity that needed to be explained.
So a couple things. One is the high school graduation wasn't in the correlation table because it's a dummy code. So you didn't have it. But in your multicollinearity table, you definitely had it. And this is the difference between treating multicollinearity as a binary thing versus a spectrum. If I have a tolerance, look at these. If I have a tolerance of 0.82, I'm not being influenced by other predictors very much. But these are comparatively pretty low to 0.82. There is some degree of shared variance happening amongst these three. Is it below a dramatic threshold that I would argue illiteracy and high school graduation are actually the same thing? No, that's what we're talking about when we're talking about tolerance below 0.2. We're saying don't put these two things in, they're redundant. They're the same. These things aren't the same, but the degree of collinearity is saying you might not need both to explain what you're trying to explain in your outcome. There isn't a threshold for that. The only reason I went here was because of the pattern I observed in the models. I saw significant, weird. Illiteracy isn't significant. That's bizarre because look at the correlation between success and illiteracy. That's really freaking high. Why, when I put it in the model, isn't it significant? I need an answer to talk about. I gotta go searching for that answer. Well, here's my answer. Once I put it in the model with this other stuff, it's only contributing about 50% unique variance. I can predict illiteracy from D1, D2, and income. In fact, I can predict half of it. So it's the answer. It's not I looked at the multicollinearity to check my assumption. I actually didn't. When I ran my multicollinearity check, this is why you can't think of running models as a linear process. It's not, oh, I ran my assumptions and now I'm going to look at my model. It's, I'm going to look at what happened in my model, and then I'm going to look at all of those other pieces to give me an explanation for what happened or why it happened. Yeah, but I wouldn't necessarily be, oh, I'm worried at a particular level until I see, oh, this is the explanation for why it happened. Does that make sense?
When it comes to, as a follow-up to that, when it comes to interpreting the recommendation for the CEO of the program,
yeah,
I'm now realizing that my interpretation might have been wrong in the sense that if you don't, Alan, I didn't note that overlap. And so I said, move your resources from the reading program to the high school graduation program, which seems fair until you start to think about, well, but how do we know what the reading program is doing for the high school graduation program? And so would that cause problems?
So it's not problems, it's just sticky. It's a sticky research question. I can't answer that without doing what? Probably more models. I want to look at, let's take income afterwards out of it. Let's just run a model with illiteracy first and then illiteracy in high school graduation. If I still don't see it, then maybe I run a model where I'm predicting high school graduation from illiteracy. There's all sorts of other modeling I can do to dig past where we are now. But based on this, all I know is that when I add illiteracy to my model, it doesn't explain any more about success. So purely based on data without thinking, That's not a bad recommendation. High school graduation timeline matters more than a literacy based on the model I found. But if you think about the fact that those things are related and that's signaled to me in these collinearity stats, then actually before I dump all my eggs in one basket, I might want to be thoughtful about, is part of when people are graduating actually being driven by literacy? In which case, if I take away the literacy program, am I going to see those high school graduation rates go down? And that's the idea of saying that's no different than saying to a principal, you should focus on high school graduation rates. What's your principal going to say back? How? That doesn't tell anybody anything. That's not programming. That's a number. So if you think about high school graduation rates and illiteracy, those aren't even playing in the same kind of camp. One is boost numbers and the other is attention to a specific program, which might boost numbers, but there's other programs too. So, I mean, this isn't a how do you do it in stats. This is how I answer this question is going to be completely different from how I answer this to the next research question. This is where I said we're out of prescription land, you know? It's fun, but it gets more fun as you kind of free yourself away from the step 1, step 2, step 3 approach. Play. Next time you do GA, play a little more. You don't have to report it. Just play to see, can I figure out really what's going on here? And the answer might be no. The answer might be, I need more data. I want to do an experiment where I test kids in the literacy program and kids who aren't in the literacy program and see, really, experimentally, does that impact graduation? I don't know. Okay? We don't know. I want to do the last assumption because nobody wants to be here all day. I mean, I would, but you don't want to be. Last assumption, homoscedasticity, the tricky but important one. We actually spent a lot of time going over this type of graph a couple weeks ago, so we don't need a lot of time here, but I just want to flag one careful thing for you. Variance is the average of the squared differences from the mean, the spread of something from its average. But you have to be careful because we talk about variance in a lot of different contexts and stats. So if you just say spread or you just say variance, you aren't necessarily, that's the 24 example. Can you help me buy this? I have 24. Great. Oh, sorry, I forgot to mention it's 24 cents. If you just say variance, you aren't necessarily talking about the specific thing we're talking about. So we have 3 types of variance that come up in regression. One is the variance in our outcome explained by our model. What's that? R squared. Yay, we love that. The second is the actual variance in our data or of a variable. Where do we see that? Where do we see that though in our output? What? No, I just want to know the variance of a variable in my data set. No, a variable, not a parameter. What are variables?
Standard error?
No.
Difference from the mean?
Standard error is the error of my parameter. Be really careful.
Correlation.
No.
Difference from the mean?
Yeah, which I see where. No, stop. Everybody draw a model. Just draw X predicts Y. Just draw that. X predicts Y. What are the variables in that model? X and? Great. If I wanted to know how X varies and I want to know how Y varies, where would I look? Thank you. I would look at my descriptives. It's just my data. Well, then say it louder. Don't whisper it. Yeah, it's just descriptive. It's standard deviation or it's variance of my actual data. Look, this is the variance explained by the model. That's the variance of variables. Why does that matter? Because what happens if we're trying to predict something that has no variance? Go home. Everybody has the same score. So we have variance explained by our model. That's R squared. We have variance just in our raw data, spread of values. Some people were high. Some people were low. Some people were old. Well, in this study, everyone was exactly the same age, apparently. Everyone was 8 years old in this study. The mean was 8 and no variance, no standard deviation. Everybody was 8. What? Yeah, I mean, I would, but if everyone's 8, then, oh, here's a great question. If everyone's 8, do I need to statistically control for it? No, I held it constant. I don't need to put it in my model. Perfect. That's a sampling control. What's the third type of variance? Error variance. That spread of the amount of error of my model. Keep those straight, because if you just say variance or spread, you aren't implying one over the other. Why did I do that? Because a lot of times people are like, oh, I want to know that the spread is the same across level of your predictors. Spread of what? It has to be the error in your model. It's constant across all level of the predictors. So here we have your observed score. Your model is going to make a prediction. Then there's other stuff. This is perfect prediction. This is a residual plot. Here's, I'm using you. There's Victor's score. There's Victor's predicted score in red. The model was off. It was way too low. It under predicted Victor's score. That's residual. We want the residual, the amount of error, to be consistent across all levels of your predictor. This one, the null hypothesis, this is another one where we didn't think, we just guessed. The null hypothesis of a Bruch-Pagan test assumes your predicted Y values are not significantly different from your observed Y values. Close your eyes, don't look at my notes, don't look at my slides, and don't blurt it out loud. What would it mean if your predicted Y was exactly the same as your observed Y? Just think for a sec. Your predicted Y is exactly the same as your observed Y. Open your eyes. What does that mean? Your model is what? Perfect. Your model predicts 7, you're a 7. Your model predicts 2, you're a 2. Your model predicts 3, you're a 3. Is that what the Bruch-Pagan does? Does it evaluate model fit? No. So even without knowing anything about Bruch-Pagan, you could have gotten this because you're, well, I know it's not model fit. I know it's not telling me whether my model is perfect. So the answer is false. Why? What it's actually doing is testing whether there's a relationship between predictor values and amount of model error. That's the null hypothesis, that these are not related. You do not want to know. I do not want to be able to do I have a line of this? Yeah. I do not want to be able to predict how well the model works based on whether your predictors are low or high. Because if I can say, oh, here's age and height. I'm predicting your height from your age. If I know you're 4 years old and I predict your height, I don't want the model to be really off there, but really accurate when you're 10. We need the amount of the model error to be the same across all levels. It has nothing to do, look at this graph. It has nothing to do with fit of the model. The model can suck and your data can still be homoscedastic. Look at this red line. That's perfect fit. Which model do you like better? The left one. But that's still homoscedastic. No matter where I pick on this predictor line, the amount of error from perfect is roughly the same. Still homoscedastic, just shitty fit. So the null hypothesis in a Bruch-Pagan is that there is no relationship between your predictors and the amount of model error. I'm going to pass on now. Yeah. Sasha, I'm going to go to my meeting. I'm half an hour late. Thank you, Raider. Did you get a hold of her? Oh.